We continue our study of number theory by now looking at rational numbers. So, a real number r is rational if and only if there exists integers a and b such that r is equal to a over b and is not equal to 0. A real number that is not rational is said to be irrational. So let's look at several examples. 10 over 3 is a rational number since both 10 and 3 are integers. Negative 5 over 39 is rational because it can be represented as either negative 5 over 39, where both negative 5 and 39 are integers, or as 5 over negative 39, where both 5 and negative 39 are integers. 0.281 is rational because it can be represented as 281 over 1,000. And of course, 281 and 1,000 are both both integers. 7 is rational because it can be represented as 7 over 1, and 7 and 1 are both integers. 0 is rational because it can be represented as 0 over 1, and both 0 and 1 are rational. 2 over 0 is not rational because there's a 0 in the denominator. Remember, the definition said the denominator cannot be 0. However, 2 over 0 is also not irrational because it's not even a real number. Remember, you're not allowed to divide by 0. Well, now what about 0.121212 repeating? Is this rational? Let x be that repeating decimal. Well, if we then multiply x by 100, we would get 12.121212, so on and so forth. So if we look at 100x minus x, notice that they both have this exact same repeating decimal. So the decimals will drop out and we're left with simply 12. However, 100x minus x is 99x. So we have 99x is equal to 12. And so x itself would be 12 over 99, which is 4 over 33. So we can actually represent the decimal 0.12121212 repeating as the fraction 4 over 33. And of course, that is rational. So yes, this number is a rational number. So in general, any decimal that terminates is rational. And any decimal that has a repeatable pattern is rational. So the zero property, you should have learned this in algebra. It states that if the product of two real numbers is 0, then at least one of them must be 0. And we're going to use this property in the following proof. We will prove that if m and n are non-zero integers, then m plus n over m times n is rational. So let m and n be integers, and m is not equal to 0, and n is not equal to 0. Right? What we want to show is that m plus n over m times n is a rational number. Right? So m plus n is an integer. I'm actually going to say m plus n and m times n are both integers. Because we have sum and product of integers are integers. Furthermore, since m is not 0 and n is not 0, m times n is not 0 by the 0 property. Well, therefore, m plus n over m times n has to be rational. Right? We've just shown that m plus n is an integer, m times n is an integer, and m times n is not 0. Since that is what we set out to show, our proof is complete. Let's now prove that the sum of any two rational numbers is rational. So let R and S be rational numbers. What we now want to show is that R plus S is rational. So since they're rational, there exists integers a, b, m, and n such that b is not 0 and n is not 0 and R is equal to a over b and S is equal to m over n. That's by definition of rational. So if we look at R plus S, it is a over b plus m over n. And remember, when you add fractions, you need a common denominator. So our common denominator here is b times n. So the numerator would be an plus mb. Now, an, mb, and bn are all integers, right? Because it's the product of integers. Furthermore, b times n is not 0 because b is not 0 and n is not 0. And this is by the 0 property. Therefore, R plus S is rational because we just wrote it as an integer over a non-zero integer. This is what we wanted to prove. And so the proof is complete. So a corollary is simply a theorem that directly follows from another theorem. So the corollary we're going to look at is the double of a rational number is rational. And since corollaries follow directly from already proven theorems, the proof of a corollary is typically extremely short. So for example, the proof of this corollary, suppose that r is a rational number, then 2r is equal to r plus r, which is rational, since the sum of rational numbers is rational. Just proved that. And so that completes that proof. And so that will conclude our study of rational numbers.